for the 2018 SARA conference is Dr. Ron Maddalena, who's been here quite some time now, I guess.
33 years and 2 days.
2 days.
Do you have the hours, minutes, and seconds?
You've worked on a number of different projects over your career, and now you're, among other tasks, you're working on Breakthrough Listen. And does everybody know what Breakthrough Listen is? It's the SETI effort using the Green Bank telescope. So
And that's telescope for us.
Oh, yeah.
So we'll get into that.
Great.
Well, thanks. Thank you very much. All right, so I've given this presentation a number of times before. And it's, presentation is the wrong word. I'm leading a discussion. Okay, we're going to lead a discussion. I'm going to lead a discussion on different ideas of the search for extraterrestrial intelligence. So this is a big audience. This is one of the largest audiences I've given this to. So I'm expecting lots of contributions, lots of comments, lots of suggestions from you, the audience. So don't ever hesitate. All right? I doubt very much this group can keep its mouth shut. So. All right, so, okay. So I've been involved in almost every SETI experiment that's been done in Green Bank since I came here 30-odd years ago. And during the course of this thing, you'll find out what my opinion is about the search for extraterrestrials. But let me find out a little bit about this group. I think I've got some ideas about where this group stands as far as the search for extraterrestrials. For example, all right, I think I know what's going to happen. I want you all to raise your hand if you agree that that you are certain that other solar systems exist. Stellar systems exist. Yeah. All right, everyone in the room. All right, good. That's a scientific fact. Okay. We got that. Okay. All right. Probably, on average, there's one planet per star in our galaxy. Okay. How many believe that Earth-like planets are common? What I mean by Earth-like planets are rocky planets that are in their star's habitable zone, the area where there is liquid water. Could be liquid water.
Common. Yeah, common. Yeah, what's common?
Common meaning that, I don't know, that it occurs, that it's not difficult to find one, that it isn't 1 in a billion, but 1 maybe in a few hundred. There are a lot of them. Okay.
There's a lot of them.
Yeah, we've detected some, which implies there's a lot, okay? Because we haven't had the ability to detect Earth-like planets until quite recently. Okay? All right, now we get into the hopefully more skeptical questions. How certain are you, how many people here are certain that extraterrestrial life exists?
In some form or another.
It's slime. I'm talking anything from slime on up.
Right, some form or another.
Okay, all right. So we have a few doubters here, right? Those who doubted, raise those who are doubters or middle of the road, raise your hands. There are a few. Okay. All right. So let's flip. How many of you are uncertain that intelligent life exists in the universe? We'll do the inverse.
Well, I'm not even sure it's including Earth.
Other places, yes. Yeah. I think dolphins, we can consider them intelligent. Human, maybe not. Okay. All right. All right. All right. How certain are you folks that if intelligent ET exists out there, that it's out there trying to communicate its existence to the world, the universe?
Are they trying?
Trying to communicate, right? Because as we'll go into later, the actual detection of just accidental signals is almost going to be impossible. They have to be really broadcasting their existence in order for us to actually see them.
Well,
That's how you get killed.
That's my opinion, but that's okay. All right. So how many think that they're out there really trying to tell the universe that they exist?
right now, or have they ever?
Ever, not now or ever. Okay. All right. 13 billion years, someplace along. Okay. So you see, the hands are getting fewer and fewer.
Well, they might have already done it billions of years ago, and then the signals just get to us, they've long gone.
Right. Okay. But that's, okay, basically I'm asking whether or not when we have an intelligent civilization, one of the goals of intelligent civilization is to make itself known. That's the question, in essence. Okay. All right.
Just as an aside, there's a whole thought process that any intelligent civilization that does that is an invitation to get wiped out by another intelligent civilization that wants no competition.
Okay, so you have just anthropomorphized. Okay? You right?
Competition is universal, even among insects.
I think it's our nature to
Okay.
advertise ourselves anyway.
Our nature.
We couldn't help, we can't help ourselves.
All right. So one of the things, yeah, so I'm going to bring up this right now, okay? You have to be very careful about anthropomorphizing, okay? And the life on Earth is very competitive, right? And this is why you made that statement, right? A new species comes in for some reason, some continent collides with another, and then there's conflict, and the better species survives, right? That's what we see on Earth. That doesn't mean that that has to happen everywhere. Does it? Why? We see it, we have only one example. So be careful when you have only one example.
Well, that presupposes that resources are unlimited, because the thing that most species compete over is resources, and I've never seen an example where resources are unlimited.
All right, but you've also made the assumption that life wants to procreate to the point of complete coverage of their resources, right? That is what's happening. That is why resources can become scarce. Is because a species wants to reproduce to the point where it uses up all its resources. That is again not necessary. You can think of a life form that doesn't have to do that.
We shall agree to disagree.
But there are other life forms that do, like an anthill.
Yeah. No,
I'm not talking about. I'm talking about another life on a different planet. I'm talking about a whole different.
No, but he's saying a whole new paradigm. I know what he's saying. I just don't have to.
So in other words, it's a life that's made out of XNG instead of DNA.
Right. Yes. Okay. Skip.
So the standard terms, in the Joel's book, the meaning of human existence, right? It's defined that there are 6 species on the earth that form social groups and contribute for the purpose of the group.
Right.
Homo sapiens is one of them in the anthills, and there's 4 others, mostly insects. So I think, I just wanted to make the point that, yeah, there are other species on Earth that are examples other than Homo sapiens that do this cooperative,
Right.
social group thing.
Right. Okay. All right. All right. So let's get some more opinions. Okay. All right. How many of you folks believe that the search for extraterrestrials is not scientific research?
Define scientific. It is.
Anybody who thinks that it's not real science?
Oh, it's real science.
Okay. Everyone agrees it's real science. Okay.
It's just not going to contribute to some corporation's bottom line, so it gets ignored, but it's real science.
Okay. Is it worthwhile? Ever believe it's worthwhile?
Sure. I
Okay.
think it's a cultural imperative.
Okay. It is worthwhile. All right. Is it an imperative area of research? Do we really need to do
Just
it?
said it. It's a cultural imperative. It's one of our steps from becoming an infant civilization to moving out into a mature civilization.
Okay, let's get the opinion of the room, okay? Is it an imperative area of research?
Yes.
Is this something that we must be doing?
Compared to what?
Okay, all right. This is where the controversy comes in, okay? Okay, all right. So some of you say it's an imperative area of research. Yet, your tax dollars, probably less than $1 million per year of your tax dollars is being spent on SETI research currently. Okay, your government, your voted, the people you have voted into office have deemed the search for extraterrestrials not worth a dime. Okay, so we as a civilization, as a culture, have decided that SETI is not an imperative area of research. Regardless of what you think in this room, as a society, as a culture, we have decided that.
In some ways, it's been decided for us.
No, I mean, we voted these people into office, right? We write them letters or don't write them letters about things. Okay? So if you think that SETI is an imperative area of research, you're not doing your homework. You're not getting your politicians to contribute our tax dollars to this area of research.
But government is not society.
Hmm?
government is not society.
It's a reflection of our society. It's a reflection of our values.
Very imperfect
Not a
one.
very inaccurate one.
Well, very imperfect one.
The point is, any SETI research that's being done right now, the big important ones, is all being done by private money. Okay? All right. Individuals who have lots and lots of money are making this decision as to this is an imperative area of research.
Which is the way it was 100 years ago as well.
Not necessarily philanthropic.
Right.
Right.
Right. It is not peer-driven science. Okay? That's another, it is not peer-driven. Peer-driven means when I have an idea for doing a scientific project, I have to apply to the NSF for a grant to do that project. Other astronomers read my proposal and decide whether it is a sufficiently important science to be funded, because money is scarce. Okay? All right. So,
Is there a qualitative statement attached to the it's not peer-driven?
sorry?
Is there a qualitative assessment attached to the statement that it's not peer-driven?
Yeah, it'll
Have
give
some
money.
goodness or badness versus independent philanthropists funding United
Well, that's
Yeah, it basically means
by saying that it's worthwhile and it may be an imperative. So, it's, yeah, but it's kind of implied in what he said.
Right. It sort of implies that even amongst the scientists, SETI research is not imperative.
Well, the church was science 300 years ago, and they decided what was an imperative, and
Right.
clearly it was
That's
not.
not peer-driven.
Okay.
That's not peer-driven, that's hope-driven.
All right.
Is there
Okay. All right.
competition,
Let's get it back on track. Okay.
is there competition within the SETI funding
Oh, you
among
betcha.
scientists on who gets funded?
So
Yes.
that is,
So there is peer.
And is that peer review?
But it's not, no. Basically, it's, you go to somebody, like the SETI Institute, right? Everyone's heard of the SETI Institute,
Yes.
right? That is completely funded by donations. Okay? So it's who you know. It's who the SETI Institute goes to. Right? So they go to certain billionaires, and other people go to other billionaires looking for their money to do their SETI research. They are not. So the billionaires don't get together and say, this is, no, they don't discuss amongst themselves. It's how people approach their billionaire as to how to get themselves.
Well, there's no consortium of billionaires, that would be our government.
yes.
All right. You guys are going to be too controversial for this. All right.
Yeah, but.
All right, so the reason why our government doesn't provide much funding is because of a benefit versus cost analysis.
Cost-benefit ratio.
Right, okay. So,
And yet our government is willing to spend money on researching the sex habits of albino squirrels.
Really?
So tell me where the importance of that research is.
Somebody bought this.
it is what it is, all right? Okay, I'm going to use that phrase a few times tonight.
What about other cultures, like the Chinese, the Russians, and so forth, besides
The Russians aren't spending a dime on SETI research either. Most governments are not. Maybe China will, but it's unclear whether
There's
they're
no
going to do it.
national prestige attached to it, like the biggest radio telescope brings.
Right. Okay. So,
But it does provide one benefit, that it helps to support the hard science that these telescopes can do. In other words, without the SETI money,
right, we'd be in much dire state.
Yeah.
We wouldn't be here right now.
140 would have been shuttered years ago, right?
Okay. All right. Let me move on to a new topic.
That's for
Okay. All right.
SETI
So,
research has a benefit.
you gotta let me move on, or we're not going anywhere today. So, okay. So this is not my analogy, and we'll go back to the cost benefit analysis. So this is not my analogy. This is somebody. Bob came up with this 30-odd years ago. The search for extraterrestrials, in his opinion, was like the search for unicorns in the Middle Ages. Everyone believed that unicorns existed. There were books about unicorns, how to cook unicorns, how to trap unicorns, the benefits of unicorns. Okay? All right. Now, we now know that unicorns don't exist, right? I assume everyone realizes they don't exist. They don't, I'm sorry. They don't exist. All right. Because we did a virtual experiment. Okay? What experiments did we do to prove that on Earth unicorns do not exist.
We explored.
None.
Hmm?
Well, you couldn't
We
find,
did it. We did a virtual experiment.
couldn't find anybody who ever saw one?
That's right. We looked. We looked, right? We looked everywhere. Well, we didn't look everywhere, but we looked in enough places. We looked for unicorns themselves, unicorn bones, unicorn droppings, any signs of unicorn fossils. None. Okay? But we haven't searched every square foot of this Earth's surface for unicorns. So unicorns, in principle, right? And there could be, you know, magic unicorns that, you know, you can only see in certain, right? But there are no unicorns, all
I
right?
don't have a lot of basis for magic.
Okay. All right. So if unicorns were one every square mile, searching for a unicorn would have been real simple, right? You just search a couple of dozen square miles, you're bound to find it.
See where you're going.
If a unicorn is one every 10,000 square miles, then it's much more difficult to find, right? So the cost and benefit ratio of those two densities of unicorns is very different. And so we come up with, I'm going to skip around, okay, with the Drake equation, okay? The Drake equation was the first attempt at coming up with a cost to benefit analysis of the likelihood of a discovery of extraterrestrials. Okay? All right. That is the Drake equation, in my opinion. Now, if you go to the SETI Institute and you look on their website, they have values for all of these things in the Drake equation. If you've never, how many of you have never seen the Drake equation before? Okay. All right. One of the things is it's a product. If anything in that list of items is 0, what happens to n?
0.
0. All right. So in order for n to be large, you have to have all these values being large. All the f's are fractions. That means they never get value larger than 1. Okay. So if you use the values on the SETI Institute's website, and we're going to leave L out of it for L is the length of time civilizations are broadcasting their signals into space. You get that n equals 0.002 times L, all right? So L has to be large in order for n to be large. Okay? So we're going to be really ambitious, and we're going to say the length of time that a civilization is broadcasting in a way in which we can detect and are searching for. Let's say it's going to be 1 billion years. Okay. All right. All right. If you do that, then there are 28 million civilizations in our galaxy at the current moment broadcasting, and essentially, but the mean separation between those civilizations, because the galaxy is large, is 10 parsecs, 30 light years. Okay?
If they were uniformly distributed.
If they were uniformly distributed in the disk. Okay? Okay? Mean separation 10 light years. But, sorry, 30 light years. But 30 light years is sort of the distance in which the ancillary, if you don't consider our radar signals, if you just talk about television, radio, things like that, that is a distance beyond which no telescope of any appreciable size, an Arecibo-like telescope, would be able to detect our broadcasts, our television signals, our radio.
Even if you're off by a factor of 1,000, that's still a huge number.
What, the distance?
No, the 28 million.
Correct. What I'm trying to make the point here is that they're not very far away, but even though they aren't far away, it's still difficult for us to detect them.
Absolutely.
Okay? Unless it's something like a purposeful signal or something ancillary like a really strong radar signal.
Or an atom bomb blast. Or an atom bomb blast.
I don't think we'd ever see an atom bomb blast on a star 30 light years away.
Well, because the EMP produced by it is so enormous and so broadly spectral that it could be a detectable civilization.
Yeah, okay, so.
So you could detect the end of a
So we can
civilization.
detect the end of the civilization. All right.
You hear it click, and that's it.
Okay. All right. So that's if L is 1 billion. All right. So let's reduce the number a bit. Okay. So, and that is using what we would call Drake's estimates. Here's the lifetime of the civilization, the number of civilizations that would be in our galaxy at any time. And what I gave you was the Drake estimate, this blue line here. So if you take 1 billion and go across, you come up with the number that we came up with. Okay? But if you can see, if the lifetime of a broadcasting civilization is 100 years, and you use just moderate estimates, not the ones on the SETI Institute's website, there's less than 1 currently in our galaxy that's broadcasting. Okay? And you can actually, there is even what's called the rare earth hypothesis, where even in the whole universe, there may only be 1 civilization capable of broadcasting at the current moment. Okay? So you can see this wide range of pessimism involved in the SETI community, from the most pessimistic to the most optimistic. And we have no idea what L is for a typical civilization, since we, again, only have the 1. And it could be as short as 100 years, 1,000 years, but anything over a moderate estimate doesn't produce more than a few in our galaxy at any one time.
Wait a minute, we're one of them.
No. Don't, no.
Doesn't that skew the whole chart to the other end?
No. Just because an event happens. Right. You can, if a bird
Say there's 10 to the minus 12 when we're 1.
Okay.
We're 1 in.
Right. If a gorilla went through this door right now, what's the chance of a gorilla coming through that door? Well, it's 100%. But a priori, you cannot say what the chances of you can come up with the chance of the chance of a gorilla coming through that door would be. And it would be really, really small. Yet, if a gorilla came through the door, it would be 100%. We're here, right? We are not in the statistics here.
Oh.
So no, just because that is, right, go for it, Skip.
Sorry, real quick, it's a little bit different, but what do you feel about the longevity being long with Bracewell probes and having just 1 or 2 very advanced civilizations able to beam at light speeds with Bracewell probes, so that they could be close, but there would be the result of an evolved civilization that lasted for perhaps 100,000 years or more, a million years, spread out 100,000 light years worth of Bracewell probes.
Right. So you have to consider, what are we going to be like? Right. Right now we are been broadcasting for about 100 years, right? What are we going to be like 1,000 years from now, 10,000 years from now? Are we going to be biological? Are we going to be artificial intelligence?
Using radio?
Right. Will we be using radio or any technique that we are using right now to communicate? Would we be still on this planet with its limited resources? Or would we have to if we have this need to expand because resources, we have gotten to a population limit for our planet, that we need to expand, and we have to get off this planet, and we need to explore. So what will we be like 1,000 years from now?
Why don't we just choose 1 galaxy?
Well, we have ours.
I know, but I mean, why? When there's...
Because of the distances are so vast. And the 1 over r
But
squared.
if they're really that intelligent, is that going to be in the beam?
Right.
Right.
Right. So the question is, a lot of people only consider our galaxy because the idea of receiving a signal from another galaxy requires that civilization not only be typical, like us, but they would have to be a mega civilization. Okay. So, for example, the Russians are no longer looking for radio signals from SETI. They're looking for megastructures in other galaxies.
Like Tabitha Star?
Tabby Star is a small example of what the Russians are looking for. They're looking for infrared signals from huge Dyson spheres around galaxy clusters, not just stars.
So in what form are we broadcasting right now? You said we were broadcasting for 100 years. Is that just TV?
We're talking radio, TV, radar. Yeah. Okay.
Okay.
Yeah. So the most likely thing that someone would pick up from us right now are radio signals. But most likely, at the larger distances, it would be our radar signals.
Now, all of our TV broadcasts and stuff are turning to various spread spectrum type of things, which if you don't know the sequence, they're very difficult to receive.
Right. and so it all looked like noise as opposed to an intelligent signal.
So if ET is what the spread spectrum for everything, it's using a polynomial that we don't know exists.
Right.
How are we doing so far, Tom?
We're doing fine. It's all of
It
this
seems
stuff.
like we're having a few individual conversations here.
Okay. So yes. Our technology is changing. For example, most of our TV signals used to be broadcast outward from TV antenna. Now they're being pointed inward. So our planet is actually quieter now in the radio than it was 20 years ago. Okay. So our signature in the universe is actually... Okay. So I want to bring up another point. All right. We've been touching on this a little bit. Okay. There is absolutely two singular observations that astronomers have made in the SETI community that we cannot ever disqualify, all right? These are absolute amazing facts, observational facts, right? So what are they? One, we've never detected an ET signal. Okay? In 50 years of trying, we have never detected an ET signal.
Except the movies.
Except the movies. And the other amazing fact is, we've never seen an ET artifact. We've never met ET. There's no evidence that ET has ever visited our planet, our solar system. Okay? This is called the Fermi paradox, right? This is the obvious fact that we've mentioned, a few have mentioned that if a civilization has evolved and gotten off its planet, it will most likely populate our galaxy in a very obvious way and make itself obviously known. And we have no sign that this has ever happened. Right? Even if you think about, we say that space is large, travel times are going to be between objects are long, right? But if a civilization has run out of its resources on its planet, what would the kinds of things it would do? And one of the things I envision it would do is to take something like some large asteroid, something the size of West Virginia, put lots of people on it, thousands of people, give them everything they ever have here, symphony orchestras, Facebook, everything of any importance to people, on this rock, and then send it off. And so what if it takes 10,000 years to get to the next star? Because everything you ever wanted, your family, your culture, everything is on that rock. Right? There's no difference than living in West Virginia, where, right?
We have everything.
We have everything, right? So this is how civilizations would, but if you do that, within a few million years, you would still populate the whole galaxy.
Yeah, but research is all the game.
So where are they? Why are they not here? And the answer to the Fermi paradox, lots of people have written papers about the answers as to why we have this dilemma in the Fermi paradox, as to why we haven't seen them, is that the Drake equation, all those optimistic values in the Drake equation, well, they're just too optimistic. Something in the Drake equation must be smaller than what people have been estimating.
Much smaller.
Much smaller. Or more scary, L is short. Right? Okay? So if L is short, that might imply that there's two things, right? Their technology could be changing, or they don't last intelligent civilizations don't last very long. Either they kill themselves, or they run out of energy or resources or something that makes their ability to communicate, truncates the amount of time they are able to communicate. Okay? All right. So let's talk about, the Drake equation is definitely too optimistic because it doesn't consider certain other aspects. And I say the rare Earth hypothesis is too pessimistic, that there's something in between and we don't know what that is yet. So it's basically the same sort of equation as the Drake equation, where n is again the number of civilizations that are out there, and you have all these factors you have to multiply together. And I say this is too pessimistic because this is a bit anthropomorphizing. This is the sequence of events that were necessary to form us. What was necessary to form us? And some of these things are really rare, must be really rare in the universe to have formed us. And it's not known Which one of these things are important or not important for the development of intelligence on a planet? All right, so let's go through a couple of these things, like fraction of planets with a large moon.
I was going to ask you that one. Why is that important?
Okay, all right, now, we do know that our moon is quite large in comparison to its parent planet, right? And that must be a rarity, because we believe that the moon was formed by a collision with a Mars-like object early in the Earth's history. And so you have to say, well, okay, what's the fraction of time that a planet of Mars' size, it's an Earth-like planet, and sticks around and has able to produce a moon of this size? The reason a moon is important is when you ask astronomers, they're rather optimistic about the existence of extraterrestrial intelligence. If you ask biologists and chemists, they are very pessimistic, because they cannot understand how chemistry or biology could have gotten started in the amount of time. They know chemical reaction rates. There isn't any way that the complexity of organic compounds could have been formed on the Earth's surface in the amount of time that it did, which is less than 1 billion years. Okay? So chemists have a hard time. And then biologists even have a harder time thinking how complexity actually was able to be accomplished in such little time. Okay, so what you have to do in order to form life and still make the chemist and biologist at least not so squirmish is to accelerate the chemistry, accelerate the biology as much as you possibly can, accelerate evolution as much as you possibly can. Okay? And a large moon provides tides. Most planets don't have the kinds of tides that we have. And biologists believe that in order that life may have formed originally in tidal pools where water comes in, brings in fresh chemicals, water rushes out, the chemicals can percolate, it's still damp, so the chemicals can still move, and chemistry can be accelerated in tidal pools faster than it would in the open oceans. All right? So you need this tide to rush in new chemicals and move away the liquids so that the chemicals can then percolate and do their thing.
Panspermia is out of fashion. Panspermia is out of fashion. The fact it might have been organic.
But you still have to form it. You still have to do it,
But
right?
they might have been somewhere else and landed here, kind of thing.
Right. You still have to form it, right? Okay. So that's one. Okay. Yeah.
Yeah, don't they also think the large moon creates a more stable orbit and therefore changes the...
Correct. So yes, we don't want our axes to tilt.
Right.
But it does. We also want seasons. Because with seasons, it means that species have to be more survivable. If we didn't have seasons and something happened to the planet, then species like a rock hitting it or something, then we would probably have more devastating mass extinctions. Okay. Okay. We need an outer Jovian planet. If you look at the Kepler planetary systems that have been found, most of them have large planets inside. The Jovian planets are inside the orbit, equivalent to the orbit of Mercury, right? So Jupiter, which is out there, 15 AUs or something like that from the center of our solar system, is now within 0.1 or 0.2 AUs of the planet, of their sun.
I have questions about the selection factor for the Kepler-type searches, because all of these Kepler-type searches involve looking for transiting objects with fairly short periods, because these short periods will show up with reasonable frequency and you'll get a lot of transits to determine that you're actually getting a detection out there.
So you won't find the Jupiter
a
that's
long
out there.
period object, and long means longer than 6 months or a year or so. You're not going to get too many of these, and they're going to be very, very hard to detect. And even with the Earth, we have a transit frequency of a year, and that's a pretty long distance as far as a Kepler-type search is concerned, and you're not going to see very many of these.
You're not going to see many of them,
right. Factor that is going to wipe out your hypothesis right there.
But if you look at 90 stars and 88 of them have Jupiters within the orbit of Mercury, that leaves only a few percentages where there can be, okay? Because the point is not that the planets, okay. So we know Jupiter cannot have, these Jovian like planets could not have formed so close to their star. They have had to have formed out beyond the ice belt where Jupiter currently is. And because of viscous processes in their stellar disk, the planets migrated inward and came into their close proximity to their star. And in the process, they would have destroyed the Marses, the Venuses, the Mercuries to get where they are. So if you find most planetary systems have stars, have planets that are close into their stars, then those planetary systems do not have any more rocky planets outside.
Why isn't the Drake equation anthropomorphic?
It's not necessarily.
It's not as anthropomorphic as this. It's a matter of degree.
But we're assuming that we're going to have carbon-based life form, and it could be silica or some other.
Right, but the Drake equation has no basis as to, doesn't make any assumptions about the form of life or the form of intelligence. All it's saying is that it's broadcasting in a way in which we can detect. That is the only anthropomorphic part of the Drake equation.
Quick question, will you eventually get to the idea that life outside the Goldilocks zone on moons and outer planets could also be in those?
The Goldilocks zone of the galaxy or the Goldilocks zone of our
Of the solar system.
of the solar system? Yeah, that's the other, well, yeah, we always have the fact that you...
Not just the Goldilocks zone, it's also the outer planets with moons and other...
Right. So there's lots of people coming up with ideas, right, as to where life could form, right? But again, if you put any extra hindrance on the formation of life, then you again are now butting against the chemist, are making it even harder for chemists and the biologists to understand how life could form. Okay, so as a first analysis, you really have to say, how can I come up with ways in which you can accelerate the formation of life, right? If you say methane, okay, life that's silicon. Well, silicon is almost as good as carbon, but it isn't as good as carbon in forming these large chain molecules, okay? So silicon life could exist, but it'd be much more difficult to form it than carbon-based life. Okay, at least the biologists tell us that. Okay. So yeah, this fact we need, so we have Jupiter has not migrated, right? And very few solar systems that we have found have Jupiters that far out, right? And Kepler's doing transit, but there are other ways of finding planets too. Other than, right, we have radial velocity measurements too, right? And so something must have stopped Jupiter from migrating inward, because the most likely thing to happen is for Jupiter-like planets to migrate inward. And the only reason we believe that Jupiter didn't migrate in is because we have Saturn. Saturn and Jupiter are keeping themselves in commensurate orbits and are preventing themselves from migrating inward. So now we need the rare occasion of a Jupiter and a Saturn in commensurate orbits to prevent the destruction of the planetary systems from which life could eventually form. Okay? You also need a Jovian planet to keep your inner solar system safe from mass extinctions. Right? If Jupiter weren't there, we would probably have mass extinctions at a higher rate. And we want mass extinctions because mass extinctions promotes evolution. But you don't want too many mass extinctions to the point where evolution isn't able to develop between mass extinctions. Okay. Stable orbits, you need a fast rotating planet. People believe a magnetic field. Mars doesn't have a magnetic field. The sun stripped its atmosphere because of that. You need a planet with a strong magnetic field. What planet in the solar system has, how often does planets have strong magnetic fields? Why does the Earth have a strong magnetic field? Did it have to do with this Mars collision? Plate tectonics. Plate tectonics is necessary to accelerate evolution. If we didn't have plate tectonics, probably evolution would not have been as fast. We wouldn't have evolved as fast. Okay? So those are the kind of things people consider now necessary for us to exist. But it doesn't mean that all these things are absolutely necessary conditions for life to exist, intelligent life to exist elsewhere. Okay. So there's two things. One important thing was the development of life 1 billion years after the Earth formed. This is basically where I'm going to leave off, because there are a couple other things we can talk about, but this is it. So there's a formation of life in a very, very short amount of time, 1 billion years. But after that, for 3 billion years, life on Earth was just single-cell organisms, nothing more complex than that. Okay? And then biologists came up with this endosymbiotic event, okay, which was necessary in order for more complex life forms to exist. Right? It happened only about 1 billion years ago. It happened only once. Okay? There's 2 once events. There are no second life forms on Earth, right? We've all evolved, every life form on Earth has evolved from the same beginnings. There isn't like life formed down deep in some ocean trench, and some life form existed on the coast of what would become Alaska.
That we know of.
There's never any evidence, we have no evidence that other life forms have formed on Earth other than the one.
That we know of.
Well, yeah. Well, you can speculate about unicorns that disappear when you look at them too, okay? But the science so far says that there is no other, right? So you can speculate and you can look, and people have looked. And every time they look, they come up with the same thing. We have all evolved from the same life species. Right? We've all descended from the same events. All right, so there's the one event where life formed on Earth, and there's the second event, which is this endosymbiotic event. And biologists have no understanding of how this could have happened. This is where 2 cells merged together. One broke through the cell wall of another, and the cell that ended up inside, and usually when this happens, and it does happen, the cells die, right? There's no reason, when you pierce a cell wall, the cell dies. For some reason, this cell survived. And they were, and then there's 2 cells were now living, one were living inside the other, had an advantage, okay? The cell that is inside the other cell became what we call our mitochondria. It is why we're able to process energy so more efficiently than single cells. Without this event, multi-cell life forms could not exist. And it happened just once. Just once in the 5 billion years. In the 4 billion years of life, it happened 1 billion years ago. And we, as complex creatures, owe our existence to this one event. All right. And you can go to, there's a really great Radiolab conversation about this.
You're saying there was just one cell, literally one.
One cell. It happened once.
Kind of like the Big Bang.
Because every time biologists think of this, they say the cell would never have survived.
Yeah.
Right. Right. Okay. So this is so it isn't like all complex creatures really developed soon after. No, everything was simple, slimy little one-cell things for 3 billion years. This is necessary, at least for us.
How did the chemists say DNA developed?
They don't know. They don't have the reaction rates necessary. The reaction rates are too slow to produce something that complex. So that's why I'm always, when I talk about this, you have to come up with ways. When you talk about, oh, life could have formed this way, that way, yeah, sure, it could form in silicon, it could form in a methane environment. But you have to, it might happen, but it might take 50 billion years for it to happen, which is not, right? We did it in a much faster way, right? And we're trying to talk to ET, which means that they must have happened, it has to have happened as fast for them as well. So the only way to do that, in my opinion, is carbon-based, liquid water, and accelerate the chemistry, biology, and evolution, right? You have to, if you're talking to somebody, if you want to communicate with somebody, it has to be in an environment in which all those things had been accelerated. Okay. So, am I a pessimist or an optimist? What do you think?
Realist.
A realist.
I'm a realist. All right. I'm saying I'm a SETI pessimist, all right? But I've been involved in almost every, as I said, I've been involved in almost every SETI experiment we've done here, right? And that's because if you don't do the experiment, you won't know.
So you're pessimistic, but hoping you were wrong. And
No.
pessimistic.
No. As a scientist, I know I come into every experiment that I do with a worldview, right? I am prejudiced, right?
Yep.
I have no scientific basis for my pessimism. I realize that, and therefore, I have to compensate.
Pessimists never have unpleasant surprises.
Well, that's true too, right? right? So I understand that I have this view, and I also understand that I have to accept that view as being a non-scientific worldview. And then I have to sort of take it one step and say, got to do the experiment. I have to prove to myself that my pessimism is right or wrong, right? So I got to do the experiment. Okay. All right. So I was going to go into the technology of it, but you guys are all over the place. All right.
Is that bad?
All right. We aren't even going to talk about breakthrough listen because we've run out of time. All right, we're done, dudes.
Please take as much time as you need.
We don't need to.
No, I don't want to. Your next talker. I mean, the guy is, whoever it is, right? Has prepared something. I'm not going to step on your toes.
10 minutes.
Thank you.
All right. So, all right. 2 minutes on breakthrough listen. It's with the Green Bank Telescope, the Parkes Telescope. It will be with other telescopes around the world. It's going to be the world's deepest SETI survey in the radio and optical. All stars within 15 light years, 1 million nearby stars at the end, 100 galaxies looking for mega civilizations. The equipment that's upstairs that's doing this experiment has 20% of the GBT's time. 1 day of observing with the breakthrough hardware is equivalent of 1 year of any previous survey ever performed. Okay? And they got the telescope 1 day to 365 days a year. They're going to get it for 10 years.
That's 25 dB better.
And it has to do not only with the size of the telescope, the amount of time they have, and also the bandwidth that they're observing. They're going to observe 5 gigahertz at a time with 1 hertz resolution, with 1/10 of a second time resolution. Massive amount. They have a 5 petabyte disk storage facility upstairs. It's going to be 10 petabytes soon. All right, they collect about half a petabyte a day. So it is the radio survey. I can guarantee you that at the end of the survey, if no one has detected ET, no one will ever try again for quite some time during radio. All being funded by Yuri Milner, a Russian billionaire. Not even an American billionaire, Russian billionaire. Ooh. All right. So it's part of the breakthrough initiatives. So you have some very famous names here. Yuri Milner, as I said, is the millionaire that's funding this particular aspect of it. This is the oversight committee. So you have people like Frank Drake and Druin, some of you may know, Stephen Hawking, the late Stephen Hawking. But you have other kind of off the wall names like Seth MacFarlane. Seth MacFarlane, yeah.
He's the family
The Seth MacFarlane, yeah. Yes. Lord Martin Rees, a knight. Magnus Carlsen. Anybody know who Magnus Carlsen is? He's a current chess champion of the world. Okay. So you have this really diverse group of folks who will put their name on the breakthrough list. And
John Brownlee or Peter Ward up there either.
yeah, I know. Yeah, I met Peter. Yeah, right. He used to run JP. No, Ames. Okay. So, so data rates 400 gigabits per second. Okay. So they're still trying to develop better and better search algorithms, because here is, for example, frequency, and this is the intensity, and this is all human-made RFI. And if you did what's called a waterfall display, so here's frequency, the dots indicates, then here's time. So each dot indicates a hit. So you have these streaks through here. These are all human-made RFI signals. What you look for, since the Earth spins and rotates around our star, what you look for is a Doppler signature, a change in frequency with time. Because they're moving and we're moving, we don't expect them to be stationary. If the signal is stationary with respect to us in velocity and frequency, then we know it's usually going to be human-based. Right. There are other sciences that Breakthrough has done. For example, it has used its equipment to find fast radio bursts. So here's just sort of all the press releases that came about from that. Right. So this is a signature of what one of these fast radio bursts look like. You can see there's frequency versus time. This is the signature of the fact that the interstellar medium has a dielectric constant that is electrons. Right. So it sort of arrives at different frequencies at different times. This is another signature that people use to determine whether or not they have an ET signal, because it has to pass through the interstellar medium. So we already talked a little bit about that. All right, and of course, we talked about what the consequences will be. We talked about this a little bit earlier. Is it going to be that ET is going to be benevolent and tell us everything we need to know? This implies that ET has empathy. There's no reason why an extraterrestrial intelligence should have empathy. You really care about us.
Yeah, that's anthropomorphizing it.
That's anthropomorphizing. And this also anthropomorphizes as well. That they will want to eat us. Right?
The natural pessimist in you should favor the one on the right.
And the other question is, the distances are too far. They probably wouldn't come and do either one of these things. And even in their, how do we even decode and understand their messages when we receive them, right? There's a nice little cartoon here. Hang on. That's Tabby Star.
Is it the angry monkey one?
Yeah, no, this is there we go. This is the ant one, okay? We're the ant, right? How do we talk to, we can't talk dolphin, right? We can't talk ape. How are we going to talk ET? Right?
So there's a similar one, and it shows ET explaining to a naked human standing in a spaceship with him the Fermi paradox. And he says, now, I know this is hard for you to understand, but imagine an angry, confused monkey who's developed very powerful explosives and amassed huge stockpiles of them. He looks out his window and he wonders why he doesn't see anyone. In fact, he never sees anybody in the neighborhood. Do you get it?
Yeah. All right. So, I'm 10 minutes over. I think we should stop at this point. I'm more than happy to talk to you over lunch or wherever you can catch me over the next day or so. Thank you for your attention, your conversation. This has been a very lively group of folks.
We are also broadcasting live, and we have viewers. And there is one question from the chat. Somebody asked, are you collaborating with SETI at home for any of your technology?
Okay. So yes, so there are a couple of ways in which we do SETI, one of which is the Breakthrough Listen way, where they pick the sources and purposely point the telescope at the objects that they look at. And then there are commensal SETI projects where they just snoop on whatever the astronomer is doing and look at their data, not for the thing that the astronomer is looking for, but for SETI signals hidden in the same path span as what the astronomer is looking at. And yes, we have what's called SARA 6. It's another backend, another detector in that control room whose data is being sent out on SETI at home. So yeah, there's Arecibo and us are probably the major sources of data for SETI at home at the current moment.
And there is another one. Are you looking for any signal, or does your search include detection of modulation?
Of modulation? Yes. Yeah, so there are the CW signals, which are things that constant wave, really broadcast narrowband signals without modulation that are, we hope, are the kinds of things that we would send out to get people's attention, or someone else's attention, and that signal would, in some way or other, steer us to where the real message would be. So we're looking for both the constant wave signals, and we're also looking for modulated signals, the kinds of things that we are broadcasting. Even when we do radar, we chirp the radar, right? And so we're looking for all those kinds of things that we produce in the intelligence signals that we send out that has information on it in the signals we receive from space.
And now my question. In the first part, when we discussed about how life has begun, you didn't consider a chance that life may have been contaminated to the Earth from a meteor or from other places.
Right. So to jumpstart the chemistry, you might consider that many of the organic compounds that are more of the complex organic compounds wrote in on comets or something. So one of the experiments we do here quite often with the GBT is look for complex chemistry that's forming in interstellar space. So we find quite complex. We found alcohols, we found sugar in space, formaldehyde, water. We find all these chemicals in space. Some of them are organic life, because organic chemistry happens very easily in interstellar space. So it is possible that they wrote in, that the chemistry wrote in on a comet, but it's, there's no, we can still think about panspermia, where it formed, life formed someplace and was transported here and contaminated the Earth. But you still have the same question: is how did that life someplace else form? Right? You still have the first origin kind of thing.
Unicorns.
So so a lot of people are considering that chemistry on Earth got jump-started because of the arrival of more complex chemistry from space, and we're looking for that chemistry.
One of the more important effects of the SETI program is that it provides some budget to help keep the NRAO open.
Right, yeah, that's true, yes. But you have to understand, because they bought time on the telescope, that means there's less time for other science as well, right? There's only so many hours in a year, right? So, yeah, we need a second telescope. So we need another billionaire.
You may never discover something else in the search.
We just need a few $100 million. That's all.
200 million. Oh, you're optimistic.
All right. Anything else, folks?
Are we transmitting?
No.
There is, yes, there are some people who are wanting to transmit, and so they're coming up with what's called METI, the messaging of extraterrestrial intelligence. And so there are organizations that are coming up with messages and ways to send out those messages out. It's how can I put it? That's, if SETI is on the fringe of science, METI is even on the fringe of SETI.
They're a little cart before the horse.
Right. Because again, there's an ethical question of should we do that? Right. What's the consequences?
It's the dinner bell for somebody else.
Is it the dinner bell for somebody else, right? Right. And who is this person to speak for the rest of humanity?
Right.
Right. What are they telling ET? Are they doing it in a way the whole world would agree upon?
We have tasty animals here.
Okay, that's it. We gotta go.